Hi, everybody. So today we're going to continue what we've been talking about this week, which is what are called two manifolds. A manifold just means a space which is smooth, which you can think of as meaning it doesn't have any cone points. And the two is the dimension. So in this class, we're only talking about surfaces, so that's why we're talking about dimension two manifolds. Just means surfaces. And I want to emphasize that I'm assuming you've already watched the office hour videos from Monday and Wednesday in this lecture. So if you haven't seen those, before you watch this, go to Canvas and watch those, because those were the lectures from Monday and Wednesday. So yeah, please watch those before you watch this. Otherwise, it probably won't make as much sense. Okay, so the idea that we've been working with this week is we want to study other examples of surfaces. So far, the main surfaces we've looked at are the plane, the hyperbolic plane, and the sphere. And we want to build new surfaces, basically by gluing pieces of old surfaces. And the way we've done it so far is by gluing the edges of a polygon together. So let me just recall the definition that we've been studying. So a flat two manifold is a surface which locally looks like the plane. And this is from an intrinsic perspective. So if I'm a bug on this surface and I'm only looking in some small region surrounding me, like maybe I can only see a few feet in any direction. So I'm just looking at a little disk with myself at the center. That disk looks like a disk in the plane. Now, as I move around, it may turn out that it's not the plane. For instance, a cylinder is an example of something that locally looks like the plane but isn't the plane. But at least in a small region, it always looks exactly like the plane. And the main example that we've been looking at is what's called the torus. Torus, which I've just been denoting by T. And the way you build a torus is you cut a square out of the plane, and then you glue the edges together. So I'm going to glue the left side to the right side, and these arrows are just telling me I glue left to right, and I glue the top to the bottom. So I glue the single arrows together, and I glue the double arrows together, and I glue them in such a way that the arrows match up. So in this example, I'm not twisting before I glue. And what we learned on Wednesday is if I want to check that this is actually a flat two manifold, I want to check that every point looks like a region of the plane, what I really need to worry about is the corners. The corners of the polygon. And what I mean by saying problems can occur is these are the points where I may not have a flat two manifold. So, if I'm a bug and I'm standing in the middle of the sphere, in the middle of this square, then obviously a little region around here looks like a region of the plane because I'm in the middle of a square and the square was cut out of the plane. Similarly, if I'm on the edge here, it's also kind of obvious because I'm gluing one edge to some other edge that after I do that gluing, that region just looks like a little region of the plane. So those points are fine. If I take a polygon and glue the edges together in some way, then the center of that polygon and the edges of the polygon are always going to look like the plane locally. What I need to worry about are the corners. So for instance, this corner, If I'm just looking at this corner by itself, the little region here looks like, well, it looks like a 90-degree corner. But then I remember the gluings. So the left side got glued to the right, which means this corner gets glued to this corner. But the top gets glued to the bottom as well. So this corner gets glued here, and the upper left corner gets glued here. And then after this gluing, I see that what I've done is I've glued these three 90-degree corners together. And so this blue dot actually, small region around it, looks like three 90-degree angles glued together, which is just a circle in the plane. Another way to say this, another way to look at this is, just like we did with cones, there's nothing special about this particular way I've glued everything together. So I can make cuts and re-glue as long as I remember where I cut. So let's say I make two cuts like this. Then what I'm saying is I'm now viewing this shape as being built out of 4 triangles rather than out of 1 square. And the triangles look like this, right? And I just have to keep track of what sides are being glued together. So those are all glued together, and similarly, this is glued to that. This is glued to that. This side's glued to that side. This side's glued to that side. So this is another way of representing the torus, where I'm thinking of it as being built out of 4 pieces rather than just one single square. And now I can move these triangles around and glue them back together in certain ways. So, for instance, now I can glue this side here to this side here, and I can visualize it more easily. So if I do that, looks like this. I moved the left side over to the right so I could do this gluing. And then I'm gonna move this piece over to here and also do that gluing. So if I add that piece on, that looks like this. So I'm gluing the double red arrows back together. And then if I move the bottom, let's see here. I'll just keep the bottom where it is too. So glue the double blue arrows back together. And then we have this. So the point I'm making is there's different ways of representing this torus. After doing all this cutting and gluing, what it looks like is now a parallelogram. And you notice that, so the bottom red arrow here is getting glued to the bottom red arrow on the right, same with the blue to the blue. So that's just saying that the left side gets glued to the right side with a twist, with no twist. And then the bottom side's getting glued to the top side. So this is exactly the same space. I'm just representing it in a different way. If I wanted to get back to the previous representation, I would just have to make these cuts like I had before and then rearrange things, and I could get back to the square. So there's different ways of drawing this. So one other way I could do it is I could cut here and cut here. And if I rearrange things that way, I'm gonna rearrange these squares so that the blue dot is in the center now. And so what this looks like, let me label these A, B, C, D. So what this would look like then A is now here, and C I moved up. B is this one, I moved it over here, and D up to there. And so the double arrow part was here, and the single arrow part was here. And of course I'd have to remember how things were glued. So let's say that's glued to that. That's glued to that. That's glued to that. That one's glued to that. Then this is the double arrow here. C's glued to D that way. And I have these here. So again, all this is saying, is that the double orange arrow gets glued to the double orange arrow without twisting, since they're pointing in the same direction, and so etc. And so the left and the right sides are getting glued together, top and bottom are getting glued together. But what's nice about this rearrangement is this blue point, which was the corner, has now been moved to the center, and so now I can easily see that this region really just looks like a region of the plane. Okay. So there's many different ways of representing these flat two manifolds, and I can get different representations by doing cutting and then regluing. Just like we did with the cones, actually. So now let's talk about a non-example, kind of see what can go wrong. So first, it's going to look similar. I'm just gluing the sides of a square together, but now I'm pointing the arrows in different directions, which means when I glue, I need this to match up, and so it means when I take this left side here, I need to twist it. So I need to send the bottom up and the top down, so twist it, rotate it up by 180 degrees before I glue it to the right side. So if I just did this gluing, I would have to twist it around so that the left arrow was pointing down when I glued it. And so this gives me a Mobius strip if I just did this gluing. So that's kind of what it looks like. You can imagine taking the left, twisting it over, and gluing it to the right. But I'm going to do more than just the Mobius strip, because I'm also going to glue the top and the bottom together. And I'm also going to add a twist when I glue the top to the bottom. Okay, so it's very hard to visualize what this thing looks like. And now we want to check, is it a flat two manifold? So if you watched the video on Wednesday, or if you attended the office hour, I think you know the answer. It's not. And remember, the problem that we need to worry about is at the corners. So what's happening at the corners now? So this top corner here, well, I'm gluing left to right, but with a twist. And so now this is the top of the one arrow, gets glued to the top of the one arrow on the right side, which is actually the bottom of the right side. And this is the bottom of the two arrow now, which gets glued back up here, because that's also the bottom of the two arrows. So these two red points are the same after I glue together. And then this blue point, this is the bottom of the one arrow and the top of the two arrow. That gets glued to the bottom of the one arrow and the top of the two arrow. It's glued like that. Okay, and so if I look at just a small region around the red, what does that look like? Well, it looks like these two pieces getting glued together. I just moved the bottom right side up to the top left corner. And if I do that, so the one arrow was here, and I have the two arrow here, and then the other one had the two arrow going this way, and the one arrow going this way. So I'm going to take this piece and flip it over. I guess you could say reflect across this line. So if I then flip it over, I can glue the one arrow together, or the two arrow, sorry. Glue the two arrow together. And now it looks like that. So I glued the two arrow part of this corner together. And so you can see that what gluing is left is I need to glue this side to that side. And so this is exactly a 180-degree cone point. These are getting glued together. Maybe I'll draw it bigger here. So let's label these vertices. I'll call this V, call this W. On this surface that I've created, V and W are 180-degree cone points. Okay, so that's bad because I've found 2 points on this surface that don't have a neighborhood that looks like the Euclidean plane. They look like a cone, right? At least in the small region surrounding V or surrounding W. So it's not a flat two manifold. And the problem is these cone points. But I claim that there's actually a way to fix this, which is very clever. How can we get rid of these cone points? And I don't mean actually remove the points. Of course, we could just, cut them off, but that's not what I want to do. I want to smooth this thing out so that it doesn't have any cone points anymore. Well, again, let me cut this into triangles. Like that. Triangles, I'll call them A, B, C, and D. You say the problem. So the problem, the reason that we have cone points is that these triangles, they're all isosceles triangles, right? And the outer angles of these triangles are too small because when I glue together, V is so what are these angles? These are 45-degree angles, right? So V is given by gluing 4 of these 45-degree angles together. That's giving me 180 degrees, which is not 360. It's not enough. So the problem is that triangles have too small of outer angles. Right, these red angles are small enough that when I do this gluing, I'm not getting 360 degrees around V, I'm only getting 180 degrees. So really what I need is these angles to be larger. How much larger so that I don't have a cone point anymore? Well, V has 4 of these glued together, so I need to not have a cone point. I need 360 degrees, gluing 4 of them together, so I need each of them to be size 360 over 4, which is 90. For V to not be a cone point. I mean, then when I did the gluing, I'd have a cone point of 360 degrees, but that's just the same as not a cone, just a flat plane. Okay, but I'm also gluing. When I glue these four triangles together, I'm gluing the tops of each of these isosceles triangles together, 4 of them. So I also need this blue angle to be 90. Otherwise, this middle point here would be a cone point. So I still need the blue angle to be 90 degrees as well. Okay, and so the idea is, if all these angles were 90, then when I glued them together in this way, I wouldn't have a cone point anywhere. I'd have no cone points, so it would be a smooth surface. So I need to use triangles whose interior angles are all 90 degrees. Okay. And of course, if I create this shape by cutting triangles out of the plane, there's no way to do that because the interior angle sum of a triangle in the plane is 180 degrees. But we have spent a lot of time studying a place where there are 90, 90, 90 triangles, and that's on the sphere. So I can't create these in the plane, but I can cut 90, 90, 90 triangles out of a sphere. And if I do this, I have no cone points. So what does this look like? I'll kind of draw it like this. I want triangles, 4 of them. So that all the interior angles are 90 degrees on these triangles. And, oops, if I do that and then still glue these edges together in the same way with twists, this space is smooth, it has no cone points. Now it no longer is a flat 2 manifold because no region, no point in here has a region around it that looks like the plane because we've cut these triangles out of the sphere. So locally this looks like a sphere, not a plane. And so this leads to a new definition. A spherical 2 manifold is a surface which locally looks like the sphere. And you can, as you can imagine, you can do the same with hyperbolic space. So I could replace spherical with hyperbolic. To get another kind of 2 manifold. So there's sort of 3 different categories of surfaces we can look at. Those which locally look like the plane, those which locally look like the sphere, and those which locally look like the hyperbolic plane. Now, what does this shape or this surface actually look like? It's kind of hard to imagine, but intrinsically it makes sense. I cut out 4 90, 90, 90 triangles and I glue all their sides together in this way. One potentially easier way to picture it is the following. So, where's an easy way to get 4 90, 90, 90 triangles? Well, I just take one of the hemispheres, right? So let's say I take, the southern half of a sphere, and if I divide it into 4 quadrants, that's my 4 90 90 90 triangles. Right, and in this picture now, I can identify the South Pole with the center right here. Those triangles are already glued together the way I want. And the extra thing I need to do is glue these edges together with a twist. And another way to say that is really I'm taking the front side here and I'm gluing it to the back side with a twist. Okay, and what happens to this corner point here? Well, this is 180 degrees right there. It's getting glued to this corner point, which is 180 degrees, so it's not a cone point. There's no cone points on here. This surface, this smooth, so this is an example of a spherical two manifold. Maybe I'll write that. Has a name. It's called the real projective plane. Okay. So maybe I'll say one more thing. I was debating whether or not to say it, but maybe it's worth it. There's another way to think of this surface that we've created. By the way, I should tell you, shorthand, it's denoted boldface R for the real numbers, P for projective, and then a 2 because it's two-dimensional. So sometimes it's denoted by RP2. To build it, another way to build it, different from what we just did, you can take a sphere which let's call it S, and identify all antipodal points. And antipodal just means points on opposite sides of S. So for instance, the North Pole gets identified with the South Pole. This point, I go through the center of the Earth, see where I come out, gets identified with that point, etc. And if I make this identification, in other words, I glue all antipodal points together, what do I get? Well, I end up, if you think about this, then every point in the northern hemisphere is identified with a point in the southern hemisphere So I can sort of forget about those points because they're already, as a set, this set of points on the sphere after doing this identification, every point in the northern hemisphere is already getting counted since it's identified with something in the southern hemisphere. And so what I'm left with is just the southern hemisphere, but I still need to identify points on the equator. So I identify this point with its antipodal, which is over here, this point with its antipodal, this point with its antipodal, etc. And you can see that under this identification, what I'm doing is I'm really gluing the front side to the back side, but I'm twisting as I glue, right? So the right side of the front gets glued to the left side of the back. And so I have to do a twist as I do the gluing. And so you recover exactly this shape here. And so this is a new surface that we haven't seen before, which locally, every point on it has a region which looks like the sphere, but it's not the sphere. It's different than the sphere. So finally, an example for you to do as homework. Oops. I want to give you another example of gluing the edges of a square together. So, I guess I should say exercise. Check if, so this is cut out of the plane, right? I cut this square out of the plane. So if it's going to be a two manifold, it's going to be a flat one. It's going to locally look like the plane. But I need to check if there's cone points. So check if this surface has cone points. Again, we checked this one on Wednesday, and it turns out it does. How could you remove these cone points? How could you remove these? By using different triangles to build this shape. For instance, triangles from the sphere or hyperbolic space. Okay. So that's exercise 1, and then let me give you a second example, which is also very interesting. A little more complicated. So this time, let's use a octagon. And I can think of this as being built out of 8 different isosceles triangles. So in the Wednesday lecture, you checked that I'm going to use colors to label the arrows since there's so many of them. So on Wednesday, you checked that this one does have cone points as well. So this is also not going to be a flat two manifold. But what I would like you to do is show that you can use hyperbolic triangles to remove the cone points. And this gives an example of a hyperbolic two manifold. So if these 8 isosceles triangles, if you cut them out of hyperbolic space correctly, you can remove all the cone points and you'll get a surface which has no cone points and locally looks like hyperbolic space. The next question, obviously, is like, what are these? What are these surfaces? What are other ways of describing them? So maybe for number 3 here, what is this surface? Like, once you remove the cone points. And in this case, it's one you've seen before. So you should be able to identify it with something more familiar. This one's a little more complicated, and that's what we'll talk about next week. All right.